We now turn to present a third structured dictionary learning method, and now our emphasis will be on shift invariance. This method is called signature dictionary learning. Everything we present hereafter is based on 1D signals due to our desire to keep the equations and the presented ideas simple. Nevertheless, all that will be said is applicable to images just the same. So with this said, here is the core idea. X is a long signal that we plan to operate on. The dictionary we are after will be used to sparsely represent small patches extracted from this signal. We would like to get a shift invariance property, which means that if two patches are shifted versions of each other, their representations should reflect that somehow. The idea we are about to present trains a signature dictionary with exactly this ability. It was proposed in a paper by Aaron in 2008. Since we operate on patches, the training set includes all the fully overlapped patches we can extract from X. By allowing cyclic shifts, we have capital N such patches, and each is of length small n. And now to the main idea. Instead of training a general n by m dictionary, D, we will train a 1D signal of length m in which all its patches are our atoms. Here is a graphical illustration of this structure. This is the signature dictionary of length m, and this is the effective dictionary built from it. Every patch in lowercase d becomes one atom in the dictionary capital D. Therefore, the first row in capital D will be the signature D itself, and every other row will be a cyclic shifted version of it to the right. We are about to formulate the signature dictionary learning in mathematical terms, and we need to define the operator Ri, which extracts a patch from location I in the signature D. This linear operator multiplies D and gets the ith atom in our overall dictionary. In our notation, Di is the atom, and it is equal to Ri times the complete vector D. This is the general objective of the dictionary learning without injecting yet the unique structure of D that we just proposed. Note that Yj is the jth patch extracted from the signal X we operate on. We are about to suggest an MOD-like algorithm in which we iterate between pursuit that estimates the representations, alpha j, and the dictionary update stage. Let's dive into these two steps. The pursuit is the easier part in our story. We assume that D is fixed, and we are after the update of the alphas. As always, this breaks down into individual pursuit tasks, each done for a patch from the training signal, and we have the freedom to choose the algorithm. Note that in the transition from a signature D to a dictionary capital D, the atoms are not normalized, and this must be taken into account when using OMP, for example. Also, since D has such a convenient convolutional structure, this could be exploited to speed up the pursuit. We will not dwell on this option here, as our focus is on the dictionary update stage that comes next. Speaking of the dictionary update, now that A is fixed, we could pose our problem in this MOD form, with an additional constraint that brings in the structure of D being circulant. Alternatively, we could pose the representation error expression in terms of the signature itself, and then the optimization could be easier to perform. Remember that for every signal Yj, we have a sparse approximation being D times alpha j. This is a linear combination of the atoms in capital D, and we have seen already that each of these atoms is obtained by the patch extractor Rk times the signature D. Thus, we get this ugly expression, which is nothing but a least squares problem with respect to the unknown D. We deviate for a minute from our story to discuss the stochastic gradient descent algorithm. It was mentioned earlier in the context of the double sparsity under the name online learning. The story goes like this. Imagine that you are facing a big least squares optimization task that is built of many quadratic expressions summed together. Let's just assume for this discussion that capital N is 1 million. The gradient of this expression is given here, being the sum of 1 million linear expressions. If we use the steepest descent in order to minimize the value of f of d, we should update d by walking in the opposite direction of the gradient. The problem with this method is that we will be accumulating 1 million expressions to get a single update of D in each iteration. The stochastic gradient approach suggests referring to the gradient expression as a mean of many elements, and so each of them could be used by itself to update D. In practice, this algorithm performs extremely well, oftentimes leading to superb results after a few sweeps through the N expressions. Returning to our signature dictionary learning story, we have a similar expression with many quadratic terms, and we could apply the stochastic gradient descent in order to find the signature D. The expression you see is a straightforward derivative of one of those quadratic terms. The implication is that we will be updating D per each patch from the training signal. When operating online like this, we no longer update all A and then update D. Instead, per each patch, we perform the pursuit to find the representation alpha j and then update D with it. Reading into the update equation, it starts by computing the representation error and then copying it with proper scales to the relevant locations in D by a process we refer to as back projection. So to summarize, the signature dictionary approach is appealing because of several important reasons. First, the number of degrees of freedom in D is m, which is so much smaller than the regular mn, and we have already discussed the benefits that this brings. This idea was originally designed for images in which the signature is a small image by itself, being the epitome of the images we train on. In this context, it was shown that given a patch and its representation, moving to its neighbor, we can start by guessing the same decomposition with shifted atoms, and then update the pursuit if required. This was found to save 90% of the computations in handling images. This is exactly the shift invariance property we started from.